Dear students, today we are starting with session number 12 for BSc program Physics subject of 3rd semester, Rani Chennamma University, Belagavi. During last session number 11, we learnt about what is aberration, what are the types of the aberration, monochromatic aberrations and circle of least confusion. Here the learning objective of session number 12 are chromatic aberration, its definition, and how to remove the chromatic aberration, that is achromatism. So after learning the session number 12, you are able to give the chromatic aberration, achromatism and achromatism methods. Here when you go for aberrations, it is the defect of a lens to make a perfect bright image of an object, and it is having two types. One is monochromatic aberration and chromatic aberration. For monochromatic aberration, it is the mono means a single color wavelength, so there will not be any colored images for a incident ray after passing through the lens. So there will be only defect in the shape, size and position of the image, whereas in chromatic aberrations the colored images plays a defect in formation of the single image for a object. So chromatic aberration is nothing but defect in the lens due to variation of refractive index with the color is called chromatic aberration, or aberration that occurs due to dispersion of light are called chromatic aberration. So the refractive index of material of the lens is different for different colors. Color means having different wavelengths, therefore refractive index plays a very important role here to have the defect in formation of the image. So hence focal length of a lens is given by 1 by f equal to product of n minus 1 and 1 by r1 plus 1 by r2, where n is refractive index of the material of the lens and f is the focal length of the lens. And since we have NV greater than NR, that is refractive index of violet ray is greater than refractive index for red color, which represents 1 by Fv greater than 1 by Fr, or Fv is less than Fr, whereas that is the focal length for violet ray is less than focal length for red color in the single lens. The same is represented by a figure drawn here. So when a parallel beam of white light falls on a lens, as you know that the function of lens is to deviate the incident ray, then there will be deviation after passing through the lens. So white light, when it passes through the lens, it bends and the violet rays will meet at principal axis at point Fv, and the red rays will meet on a principal axis at different position. So there will be different meeting points for violet ray as well as red ray, and remaining colors are going to meet on a principal axis at different positions in between Fv and Fr. So when you place a screen in between Fv and Fr, and when you move it, there will be a position. On the screen you can observe different incidents of colored images at different positions. So there is one position AB where the least intersection will be observed, that is there will be a circle is observed where AB represents its diameter. So when a circle is observed on a screen, that circle is called as circle of least confusion, and the radius of that circle is said to be the measure of lateral chromatic aberration. That is, when a circle on a plane is called a circle of least confusion, its radius is lateral chromatic aberration. So this at AB, the minimum overlapping of the colors occurs over a plane AB which is perpendicular to the principal axis. Again, as you know that the violet rays meet at point FP nearer to lens, whereas red colored line meet at far away from the lens, whose focal length is FR, and focal length for violet is FV. So the difference between FR and FV, the distance between FR and FV gives the longitudinal chromatic aberration. That is, the difference between focal lengths of a lens for red and violet is a measure of longitudinal chromatic aberration. If you want to give it in the form of equation, Fr minus Fv is equal to omega F, or omega is equal to Fr minus Fv divided by F, where omega is dispersive power of the material and F is focal length of a lens for a mean ray. And if df is difference in focal lengths of two colors, then omega is equal to df by f, where f is equal to root of fv and fr. So this is how you are going to have the equation for dispersive power of a lens. Now we will go for a chromatism. The chromatic aberration can be corrected by combining a convex lens made up of ground glass with the proper concave lens of flint glass. If a beam of white light is incident on a convex lens, red color is rendered less convergent than violet color. On the other hand, if the beam of white light is incident on a concave lens, red color is rendered less divergent than the violet color. So, by the combination of suitable convex and concave lenses, red and violet colors can be brought to a focus at a single point on the principal axis. Thus, the coloring or chromatic aberration can be rectified. So, the combination of suitable convex and concave lenses which removes the chromatic aberration is called as achromatic combination, and the process of removing the chromatic aberration is called as achromatism. So at the end of this session, you are able to answer the questions like chromatic aberration, achromatism, dispersive power, what is focal length, circle of least confusion, longitudinal and lateral chromatic aberrations.